Hey guys! So today we're starting chapter 6. So chapter 6 is on page 368 in your book, and it's called Root, Power, and Logarithm Functions. So the first section we're going to be doing is section 1. Which is called nth root functions. So we're going to learn what nth root actually means. So if you look at your notes, the first thing it says is how many real nth roots does a real number have? So we've got something that says y equals x to the n when n is odd. If I think about that, n is odd, that could be like 3 or 5. So that would be something like y equals x to the third. Okay, so how many real roots does something like that have? Well, if I were to graph that, it looks something like this, okay, like your cubic function. And when I'm talking about roots, I'm talking about x-intercepts. So how many times does this cross the x-axis? And the answer is 1. So when you have y equals x to the n and n is odd, it's going to have one real root. 1. Okay, if you have y equals x to the n and n is even, that's going to be a totally different story. So let's say I have something like y equals x to the fourth. When I graph that, it basically looks like a parabola. So it could look something like this, or could look something like this, or it could look something like that. So you can see that we've got a couple different scenarios here. Okay, the first scenario is this one down here, and with this one, how many times does it cross the x-axis? Well, it crosses twice. Okay, so in that case, we would have 2 real roots. For this blue one here, this one only crosses the x-axis once at the point 0, 0. So that one would only have 1 real root. And this red one here, it doesn't cross the x-axis. So that means that it has no real roots. Okay, so that would be 0. So what we want to say is if k is greater than 0, then there are 2 real roots. If k is equal to 0, then there's 1 real root. And if k is less than 0, then there are no real roots. Notice that I'm saying real roots because there are roots, they're just imaginary. Okay, so we'll get to those imaginary numbers here soon. Alright, so that leads us to our power of a power property, which says that for x is greater than or equal to 0 and m not equal to 0 and n not equal to 0, we can say x to the m to the n is equal to x to the m times n. So in other words, if we have x to the m to the n, okay, instead of taking that power to a power, what we can do is multiply those 2 powers together to simplify. Okay? So now we've got our nth root functions here. It says the functions with the equation of the form y equals x to the 1 over n, where n is greater than or equal to 2. That is what we would call an nth root function. Okay, so our nth root function is going to be y equals x to the 1 over n, where n is greater than or equal to 2. Okay, so basically we're thinking about like x to the 1/2, x to the 1/4. Okay, notice that 1/2, if I take the power to the 1/2, that is the same thing as the square root. So if I have y equals x to the 1/2, that's equal to the square root of x. This is why it's called a root function, okay, because we're finding a root of that x value. Okay, so the domain of these root functions is going to be positive real numbers okay, because I can't put a negative underneath the square root. Okay, that's when I get those imaginary numbers. So our domain is just positive real numbers. Our range is also positive real numbers because I can't get out a negative if I can't put in a negative underneath the square root. Okay, so we've got when x is greater than or equal to 0 and n is greater than or equal to an integer, or an even integer, okay, then we can say the nth root of x is equal to x to the 1 over n, or the positive nth root of x. Okay, that's basically what I just said. Then it says when x is less than 0 and n is greater than or equal to 3, that is an odd integer. Okay, so we've got the nth root of x is going to be the real nth root of x. Okay, so basically when you've got an even integer there, so something like this, okay, we're just talking about the positive root. Whereas if you have something like y equals x to the 1/3, okay, that's the cube root of x, that's just whatever we get out. Okay, so it could be positive, it could be negative. The way that I like to think about it is when I have something to an odd power, so let's say I have -2 to the 3rd. -2 to the 3rd would be -8, because -2 times -2 times -2 gives me -8. So if I take the cube root of -8, I get -2. So with odd powers and odd roots, I can have negative numbers, whereas with even powers and even roots, you cannot have negative numbers, okay? So think about it this way. If I take -2 squared, okay, -2 squared is +4. So if I take the square root of 4, I would get a +2. The square root of -4, that doesn't exist, okay? That's an imaginary number. All right, let's start working on these practice problems here. So the first one we have is 64 to the 1/3. So another way to think about that is that it's going to be the cube root of 64. So I'm going to say something to the 3rd power makes 64. This is one that you should memorize. Okay, so something to the 3rd power makes 64. That is 4. Okay. Next one we've got is 36 to the 1/2. So remember, to the 1/2, that's like saying the square root. So this is the square root of 36, which, again, you should know this one, is 6. Okay, the next one, we've got the cube root of -343. Okay, this one I don't expect you to memorize. So what you can do is you can plug this into your calculator, and we know that even if you don't know how to do the cube root on your calculator, you can always do a power. So the cube root is the same as to the 1/3. So in our calculators, in parentheses, put -343 to the 1/3 power. Make sure your 1/3 is in parentheses. Okay, and what you should get is -7. All right, the next one, we've got the 4th root of 16. So again, you're thinking about something to the 4th power makes 16. Okay, so I know that off the top of my head. Hopefully you can figure it out pretty quick. It's going to be 2. All right, so the next part, we've got a regular tetrahedron is a pyramid with 4 equal edges of length s. Its base is an equilateral triangle with area B equals square root of 3 over 4 times s squared, and whose height, h, equals square root of 6 over 3 times s. We want to give a formula for the volume V of a regular tetrahedron in terms of the edge length. Recall that the volume of any pyramid is V equals 1/3 base times height. All right, sounds fun. So I'm going to start with my volume formula, and I'm going to plug in the other formulas that I know And I'm going to try to get this in terms of S, which is my edge length. So I've got V equals 1/3 base times height. I know that my base is square root 3 over 4 S squared. And I know that my height is square root 6 over 3S. So this is going to be my volume in terms of edge length. Now what I need to do is simplify it down so that it actually looks nice. Okay, so if I multiply this stuff out, remember that you can think about all this stuff as everything in the numerator gets multiplied, everything in the denominator gets multiplied. So in the numerator, I'll have 1 square root 3 S squared, square root 6, and S. And in the numerator, I'll have 3, 4, and 3. Okay. So square root 3 times square root 6, that's the square root of 18. And S squared times S is S cubed. 3 times 4 times 3, that's 12 times 3, which is 36. I can simplify this radical here. So 18, I know that's 9 and 2. So that would be 3 square root 2. So now I've got 3s cubed square root 2 over 36. If I simplify this 3 and this 36, this becomes a 12. And I have s cubed square root 2 over 12. Ta-da! Okay, next up, give a formula for the length S of a regular tetrahedron's edge in terms of its volume. So now I want a formula that's S equals, and it has the volume in it. Okay, so S equals something with V. So I'm going to start off with this formula where I left off, and I'm going to solve this for S. Alright, so right now I have V equals S cubed square root 2 over 12. If I want to solve that for S, I need to get everything away from S. Okay, so I'm going to start by multiplying by 12. So I'll have 12V equals S cubed square root 2. Okay, then I'm going to divide by the square root of 2. And I know I need to rationalize that, but I'll worry about that later. Okay, so now that I've divided by the square root of 2, I have S cubed equals 12V over the square root of 2. If I want to get that S by itself, I need to get rid of that cube. And the way I'm going to do that is by taking it to the 1/3 power. So I've got S equals 12V over square root 2 to the 1/3 power. Okay? Now that is not an appropriate answer because I have this square root 2 in my denominator. So let's go ahead and rationalize that now. So if I'm going to rationalize that, that means that I need to multiply by square root 2 over square root 2 in here. So I will have 12 square root 2 V over 2. Then I can simplify this down. So I'll have 6 square root 2 V to the 1/3. Alright, so that's going to be my answer. S equals 6 square root 2V to the 1/3 in order to have S in terms of V.